Cool. So now, now we have WebGL 2.0, which was just recently launched in March. Again, it does take OpenGL ES 3.0 features and tries to bridge desktop and mobile platforms together. So now you can have very cross-compatible things. At the current time, when you look at WebGL stats and can I use, there's kind of a discrepancy in terms of adoption. But as Neil has said, it's kind of like it just came out 2 or 3 months ago, so it's really picking up speed. It's currently available in version 53 of Firefox as well as Chrome 58, and it intends to ship. And you can click on the link on how to get the WebGL implementation working for yourselves for more details on that. Hello.
Yep.
Yeah.
It just shows you the WebGL 1 and 2 and different browsers that support it. Okay.
Yeah. So there's I definitely recommend looking at kind of like the can I use links in particular because they kind of show you where everyone is in terms of adoption across the different browsers. It's kind of a fascinating graph. So next.
Yep.
Okay. So what's new? There's a bunch of different things. Obviously there's a lot of texture support. There's a lot of texture formats, and Xavier's going to talk about this in more detail. There's 3D textures are now available, 2D textures array, immutable textures in the sense of like not necessarily the data, but rather the memory allocation. You can have access to non-power of 2 texture support as well as seamless tube maps. So a lot of these things were extensions in WebGL 1.0 that were ported over to become core features. And so that's kind of eventually that's kind of the goal, right? We do kind of caution that WebGL 2 is not entirely backwards compatible with WebGL 1.0. There's some things that are still kind of in the process of being ported over, so yeah.
Yeah. And I guess it's worth pointing out that if you wanted to use a lot of features that's already in WebGL 1, so like instance drawing and also vertex array objects is really useful for particle simulation with a lot of instance geometries and mesh. You can do that with WebGL 1 with the extensions. So you don't have to feel like, oh, WebGL 2 is not quite there yet. But in fact, 3JS already has support for them, and it will carry the extensions automatically by default.
Yeah, that's a very good point. And I think to jump off on that, I would say that a lot of the examples we're going to show, some of them are going to be some are WebGL 1.0 with extensions. The whole point of that is to kind of show you where things are trending. And, as again, like WebGL 2.0 has just been recently available, it's really a case of like how do we get to that point where we can utilize the features that they have. They're already available in the past, but now can be accessed through the core features themselves. So.
Yeah. Okay. Mm-hmm. So the next part we're going to be talking about the techniques that we'll select about 6 or 7 different things in WebGL 2 and tell you about how to use them. So I guess I'll tell you about, first of all, textures. So in WebGL 2.0, they've got mostly the texture formats from OpenGL ES3 spec. So that spec was first written, I believe, in 2006, and they've listed that to make it available. The important part here is they've added depth textures. So if you want to use textures to store depth in full precision in terms of 32-bit integers and floating point, you can do that. And they've also added a lot more different texture formats, so you don't have to convert integers to floating points, which is not perfect, and the other way around as well. So any texture that you have that you want to load into WebGL, you can be sure that the bytes are exactly the same, which is really, really cool if you want to have really precise computations and store it as some kind of data set. And later on, we'll also talk about the shaded access, but you can query the texture size as well as the texture pixel value as well by however UV or any coordinates that you like. So you can kind of use textures not only just as a interpolation thing, but also you can use it to query and store stuff. So in terms of textures, we also have 3D textures that's now available in WebGL 2, as well as 2D texture arrays. So you can think of instead of just width and height, you have now a depth, or in terms of width and height, you now have a length, which if you are doing volumetric rendering for medical applications, that's really useful. And if you wanted to load a texture that's slightly taller, like a sprite, and you might be making an HTML5 game, then non-power 2 textures makes it really useful because now you don't have to load a texture that's just off that square, and then you have to make it in the weird ratio to make it work. You can just load it, and the driver will go, okay, I'll allocate the exact size you need. And the next thing in terms of optimization is immutable textures. So in the beginning, you can say, hey, my game needs 32 megabytes of textures. This is all their sizes and everything. You can just allocate it right away as your game plays. So you don't have to keep sort of allocating textures throughout the time. And you can even, like on say before, you can swap out a data set. So if you need to change the character states, you need to kind of add something to it, you can just modify the textures by pointing it to a different data set, but the allocation will be there on the GPU. So this kind of saves you having to go back and forth again in another round trip. And there's a lot more features you can get in terms of like sRGB for linear interpolation. If you're doing some kind of gamut interpolation, it's really nice to be working in a linear state. And the other thing about the very bottom one is the common compressed textures. So there's two formats, it's ETC2 and EAC. They're actually not in WebGL 2, but they will be available as an extension. So if you're using some kind of specific compression formats that you want on the GPU, that will make it available for you should the device have access to that extension. And I should also mention that the text shaders can also access the textures too. So if you want to play with displacements by moving your textures, for example, to generate a terrain, you can do that in real time. And I'll hand over to Juan about the next bit, which is geometry.
Okay, so geometry is interesting because it's been used a lot in video games. Just to give you a background, my background is film and sometimes real time, depending on the mood. And so the thing about geometry instancing is like, say for example, you have a scene where you have a model that you're going to instance multiple times over or 10,000 times over. Let's say that you have a simple leaf that's just a few triangles, and you're kind of like, when you render it out, it's pretty instant. The real overhead that comes out from there is really kind of the rendering calls that you're making multiple times over in order to render out like 10,000 leaves, and that's going to cost a lot, significant, performance penalties. So geometry instancing is kind of an approach towards rendering multiple copies of the same mesh in a scene with a single draw call, and the intent is, hey, you can decouple the actual transformations from the actual model and utilize and kind of make it efficient in terms of like just how you already know that this stuff exists and you can just put it together in one call. So that's kind of the solution that they take. It's a big performance improvement. It's definitely great for details and set dressing like trees, grass, buildings. It's sometimes used for crowds and characters, and ultimately the goal with that is to eliminate that function call overhead. And so again, as I mentioned, kind of my background is more like in production. So all of my examples are going to be non-WebGL cases from the beginning with the intent of saying, hey, these are the things hopefully we can do with WebGL 2.0. These are the cases that's been done in games. And so for example, you have kind of mesh scattering for set dressing detail. Again, a lot of it is vegetation, rocks. Umbrellas is a really interesting case. So with Naughty Dog for Uncharted 4, they in order to create the Madagascar level where you're kind of walking through, kind of a street market, there's a lot of like vendors and umbrellas, and in order to be able to pull that off, they had to use, outside of using their usual tricks of using lighting, shadows, material blending in order to kind of create the illusion that there's unique assets. They also used instancing on their prototypes for variants in order to maintain their memory footprint. So like ultimately like the umbrellas that you're seeing in the top right really boil down to two umbrella assets, or two types of umbrella assets. One is interactive, one is not. And they're instance multiple time and given variants based on shader-driven computations. Other things that have been utilized is mesh particles, like for example, thin, long sparks. Like one great example that's been used recently in a game is Horizon Zero Dawn's utilize a GPU-based procedural placement system. And so, that system is a really well thought out approach towards assembling environments complete with sounds, effects, wildlife, and gameplay. And the whole intent was like taking 10,000 plus objects or 100,000 plus objects in the scene out of 500 plus assets, and being able to place them down in an average busy load of 250, I think, microseconds, I believe, on a GPU. And it's a GPU. I believe it's a Radeon GCN architecture in PS4. That's been out for a while, so it's kind of impressive that they're able to pull that off. Another usage of geometry instancing is in Pixar's Academy Award-winning short Piper, which has 1 million grains of sand. It's about each of those sand particles, I think, has around 5,000 polygons. So they utilized RenderMan's trim bars to derive the shading variance and day-to-wet parameters with only 12 grains of sand, and then instanced it with point clouds and scattered it across like the beach for Piper using Poisson distribution model. I didn't put it here on the slides, but Finding Dory uses something similar in terms of like dealing with procedurals. I actually worked on that team for rendering, and I can tell you those assets are ridiculously expensive, and we would not pull it off if we had to just put them, put them all individually in the scene. EA Dice instances everything with exception of particle systems. They also do a variation of instancing on regular meshes, which is characters, buildings, and props, with the instancing data being put in a byte buffer instead of a vertex buffer, and the data location being explicitly calculated in the shader itself. So those are some examples from non-WebGL cases. Instancing from WebGL examples, there are a few already available. We can show off Brandon Jones' first iteration of this is kind of the monkey picture that you're seeing below, and we can click on that. That's WebGL instancing with angle instance array.
Sorry.
No worries. And so this is actually a really good article. He discusses his process as well, and the demo is available, and so is the source code. So if you click on the actual demo itself, which I think is the picture, okay. And you can see this was all created, I think, with I think it's a 4x4 matrix or 4x4 instances of monkeys. But obviously he's instanced them across, I guess, an infinite 3D space, I guess. So that's one example. The other cool one that I really like is his next example that he showcases, which is the crowd demo. That's the picture that you see in the slides that includes soldiers. And if you click that, you can kind of see like what he's pulling off, which is
that link one is in the next slide, so I'll get to it when I get there.
Okay, fantastic. So we'll cover that in the next slides.
Yep.
So those are some examples as well, and obviously there's some simple examples that you can try out through the sample pack, I believe. So, yeah.
So I'm going to move on to the...
Yeah, let's move on. Okay, so another feature that's available in WebGL 2.0 is transform feedback. So up until now, we've always sent the Vertex data to the graphics processor and only produced drawn pixels in frame buffers in return. So the whole point of transform feedback is that it's trying to solve the idea of, or the question of, what if we are able to retrieve those vertices after they pass through that vertex processing step. And so what happens is that with transform feedback is that we can connect to a special buffer and send our transform primitives to it, and from there decide whether or not we want to send it back, continue on to the rasterizer, or we send it back to the vertex buffer in the next draw call. And so that creating a loop where the transform feedback buffer serves as a vertex buffer kind of allows for computation and data to stay purely on the GPU with no application involvement other than connecting the proper buffers for each draw and setting up some state. And that's very helpful in terms of kind of not having that overhead between switching between the CPU and GPU. And so if we go to the next slide, you can kind of see where this is very useful for particle systems. So I guess you guys know what the particle system is, but there's a definition up there. But without transfer feedback, WebGL would be copying those particle contents from GPU memory to CPU memory, make the calculations, and reload that information onto the GPU to be rendered. So managing that data transfer between the GPU and CPU, as I mentioned, and all the redundant complex computation takes a lot of time and bandwidth. Whereas if you're dealing with transform feedback, you can connect to the transform feedback buffer, apply the transformations on VBOs before rendering, have all the computations done in the GPU, and not deal with the application involvement other than connecting, again, the buffers and setting the state. So that's really good, again, for doing complex computations on the VBOs and offloads the CPU and memory retimes. So next slide.
So I'll quickly show the crowd demo that was from before, which is, I think, this one.
Yeah. Yeah, so the crowd demo, I believe, makes use of this. Again, going back to geometry rendering, again, like geometry instancing, they're instancing like a million soldiers. And what I would do actually is I would recommend playing with this demo. The lights went out on me, so that's weird. So you can't see me, but the lights went out. So I would recommend playing with this demo a bit. You could play around with the variant count.
200.
Was that? Sure, you can set it to 200. I think I set it to 1,000 one point, and it actually still works really well. You can...
So maybe that's pushing it too much.
Maybe a little bit. And you can also set the variant count, which kind of sets like the variations and then the animation clips as well. Yeah.
Yep.
So it's a really cool demo. That's one of my favorites. Other demos where you can showcase stateful particle systems, again, is the interactive particle demo that we showed you at the beginning of the masterclass. After the flood is actually a really good example of multiple like cases of different features that are being used. I would say that I've tried this on my desktop, or yeah, I've tried this on my laptop, and it's slow for me. So I would definitely just click on the video, and we can do that later when we get to like talking about games or the state of the industry in games. The Strange Lorentz attractor system is actually a really cool implementation of the Lorentz system. And so the Lorentz system is a system of ordinary differential equations first studied by Edward Lorenz, and it's notable for having chaotic solutions for certain parameter values and initial conditions. And it's ultimately a cool visualization. When you plot it, it really just looks like a butterfly or a figure eight. And you can play around with it and kind of see how to utilize transfer feedback to make this a little more simple to work with. So that's another one.
The Lorentz system is a chaos system, so when you run it in real time, as you modify it, it doesn't reset it, it just changes it, as it plays. And everything depends on the previous frame, which is also why transform feedback is so much useful, to not to have to resend it back to the CPU and calculate everything again.
Right. Cool. And of course, there's, again, the WebGL 2.0 sample packs and WebGL 2 examples that you can try out. There are non-WebGL implementations of transform feedback. Philip Rideout's GPU-based advection blog post is actually really interesting. And you can use transform feedback to capture and reuse for geometric deformations. I didn't put the picture of this, but basically it would be like if, say, you're pinching someone's cheek and you want the cheek to return to its original state, you can totally do that. One cool one, you can also do terrain generation calculations using transform feedback. If we go to the next slide after that, there's a cool example that's being used in Deus Ex Mankind Divided, and that's kind of like in the terrain, like their Titan armor. I don't know if you see it in the actual game because I haven't actually played it, but I've talked to the researchers about it, and so the whole idea of the armor is that it kind of goes up and down, it moves in waves, and so if you see it over there, they utilize that technique in order to kind of like make sure the geometry goes back to its restful state. Yeah, so that's kind of another example from games.
Yep, and we'll move on to the integer vertex attributes.
Right. So integer vertex attributes go hand in hand with transform feedback. It's just really integer texture support. The real key example for this in WebGL is, again, the interactive particle demo. I've talked to a few people about it, and basically what it does is that it requires a random number generator built around a modulus-based index vertex attributes in order to maintain state. And that's how they determine whether, a particle dies, a particle returns back to the current state, that sort of thing. And that's how they pursue it in conjunction with the transform feedback phase. More generally, you can set multiple integers into the vertex shader. You can perform logical operations on them, and then output them out for usage.
Okay, we have a question apparently. Yeah.
Does that mean that we can network particle systems?
Can you hear that? The question was, does that mean that we can network particle systems?
I would say it's possible. I think with transform, yeah, I think it is definitely possible because you can bounce them back and forth between buffers anyway. So that's my assumption. I haven't tested it out myself, but.
Yeah, but what you have to do is you have to have a host that's going to be doing the simulations. Then you send the things over the network. You wouldn't be doing that on every client to do the same operation. Yeah, okay. The next step will be rendering. So we'll start with full rendering, and I think Hong will take that one too.
What? Me again? Okay. Sorry. I was like, wow, this is like a whole set of slides where I'm just talking. Apologies about that. I really am fast. But if you have any questions, send me an email. So forward rendering is kind of the default rendering process. It comes with programmable graphics pipeline. It's fairly linear. You send your geometry or primitives to the vertex shader. This is the WebGL case. You send it to the vertex shader. It gets processed. You do the vertex calculations on it. Then you send it to be rasterized and into the fragment shader, and then you send it to your render target. It's fairly linear, but heavy on performance, as each rendered object has to be iterated over each light source for every rendered fragment. And it tends to waste a lot of fragment shader runs because basically if you have like a high depth complexity in your scene, you're dealing with multiple shader fragment outputs or fragment shader outputs that are being overridden again and again. So it's kind of not great. It's not great for games for sure. And a technique that's been utilized a lot again in games is deferred rendering. And so what deferred rendering does is it takes that that forward rendering pipeline and splits it into two. And you get two stages. One is the geometry pass, where you're taking all the geometry data and then storing them in multiple draw buffers. And then you're doing, and from there, or, it's called the G buffer. So you're storing them as a collection of textures in the G buffer. And from there, you do a second pass for lighting calculations. So you can utilize the information that's been stored in the buffers to calculate your final shading and lighting calculations. And that decouples the expected fragment processes that come at a later stage in the pipeline. And so, again, there are some pros and cons to it. Again, with forward rendering, it's very, it's very simple. It's already available. It can preserve true transparency and provide anti-aliasing out of the box. Of course, the con again is it's linear, it's heavy on performance, you're wasting fragment shader calculations, and there's potentially a limited number of bytes available for rendering. With the deferred rendering, you have the actual fragment information as a screen pixel, so all you have to do is only one fragment shader pass. It's really great for dynamic lighting and optimizing for a large amount of light sources in post-processing, which is great for games. The cons, of course, is that it requires high bandwidth in memory, and transparency and anti-aliasing requires workarounds in order to get it to work properly. It's one of those open challenges, I would imagine. So, and when you look at, if we go to the next slide, we can talk about a bit about some of the non-WebGL cases that are available. I love games, so obviously there's a lot of game slides here. And so there's real-time lighting via light linked list. I believe, which game does this? I believe it's Destiny does this. Is that correct? I think so. I could be wrong, but you should check the slides themselves. Quick plug. SIGGRAPH has a fantastic games track, and I'm not saying this because I used to be part of the game committee, but they have a fantastic games track called Advances in Real-Time Rendering, where they talk about some of the advancements that are currently being done. But if you go back into the previous courses, they talk about a lot of these things that we're talking about right now, which is really cool. And that's where I'm getting a lot of these links, actually. So Destiny does a lot of work in terms of deferred lighting. The Battlefield series utilizes SPU-based deferred shading, I believe barely since Battlefield 3. You can utilize it to do physically correct lighting models, which I believe is Killzone Shadowfall. Uncharted 4 utilizes it, of course, and you can do a lot of post-processing effects as well. Like you can do bloom, you can do FXAA, which is anti-aliasing, and you can do ambient occlusion as well. Sunset Overdrive, I believe. Sunset Overdrive is the one that does real-time lighting via light linked list. That's right. It's a really cool presentation. You should check it out. And yeah, that's my spiel on non-WebGL cases. So hopefully that's a good segue to multiple draw buffers, which Xavier will be talking about in more detail.
Yeah, so one of the common, conception is, so if you have to, just go back to the slides 2 before, if you have to draw the depth and normals and color for all the things, wouldn't that be slower? That doesn't make any sense, right? Actually, in WebGL 2, with multiple draw buffers, you can draw all of this in one draw call to multiple buffers at once. So instead of drawing, like the color face, the normal face, or whatever, it will be done all at the same time, 2 different buffers, and then you can do the compositing just before the frame gets output to your screen. So actually, if you're only using, say, 3 draw buffers, which is really common for a lot of games because they have limited bandwidth, you can get a lot more information than just RGB and maybe alpha out of your thing. So you can now contain things like the IDs for different targets, you can contain extra information like maybe shadow information and things like that. So that gives you that extra flexibility in how you want to control your rendering output. So that's why multiple draw buffers is now available as a core feature in WebGL 2. But you can get it in WebGL 1 as an extension, and again, 3JS does take advantage of that. So if you have looked at the post-processing, libraries for 3JS, they do draw to different buffers, and they'll play with blur, play with bloom, and you can render it back to the main scene and so on and so forth. And it's really, this feature is really what makes deferred rendering, available to a lot of developers. And so if you want to have that extra control, and it's pretty easy to spot like games that use full rendering. If you have gone to the graphics setting and you'll see like, oh, max number of lights, I can scroll up to 8. Interesting. But if you don't have that, you can see lights everywhere. Chances are they're using deferred rendering, because in full rendering you'll have to multiply the lights through every single geometry per light, and that's very expensive. Whereas because when you're drawing in deferred, you don't care about lights. You're just going to draw the normals. You're just going to draw the color, and then you draw the light wherever they are, and then you do the compositing later. So it's really useful. And there is a really cool demo here, which I will click So this is tile-based rendering using multiple toolboxes. And I think this was shown at SIGGRAPH, which was really, really cool. And it may take a while. There we go. So you can press like a thing to go to forward, which I think is F. So forward is like that, and it's really slow because it has to multiply all the lights per geometry. Whereas if you do deferred, you're just, you kind of decouple the complexity and you do composite later. So that makes it really viable to do lots of lights. And you can reduce the number of lights in the demo as usual, or you can just make it like massive and everything's super bright if you really want. And you can also check out their different passes. So you have depth, which is really useful if you want to, just kind of have fake fog. All of a sudden, it comes to you at no extra cost because you already have the depth in your scene, and you can do normals. You know where things are pointing for lighting, and you have other things like the positions. If you need to use the world position for something, you have your color or albino for the rendering computations and so on. So I'll go back to the slide. All right, so the next thing that we're going to be talking about is volumetrics, and I'll give you this one again.
Hi, so volumetrics is really cool. It's one of my favorite things. Volumetric rendering allows you to simulate the propagation of light rays into a material's volume. And so getting volumetric rendering right allows for an increase in, visual complexity and more varied visuals in whatever you're doing, like be it film, be it games, visualizations, that sort of thing. It also allows you us to converge towards physically based rendering, which means that the participating medium materials are decoupled from the light sources themselves. This means that we can deal with entities such as fog, particles, and so on in an approximately accurate way as possible. So volume ray casting, we can get to this later, but volume ray casting is kind of a technique that shoots out a ray from the camera into the material's volume for rendering calculations. And the whole way it works is that a ray is cast, and then points are sampled equidistantly along the propagation of the ray. The volume is usually not aligned with the ray of sight itself, so the sample points may be in between voxels, in which, if that's the case, you're essentially your samples are going to be interpolated from the surrounding voxels themselves, which is pretty straightforward. Those samples are then shaded based on the material color, their surface orientation with respect to local surfaces within the volume, and the location of the light sources in the scene. And once that's all done, all the samples are composited along the ray of sight and allow you to result in a final color value for that pixel that's currently being processed. I know I should give you a caveat that I'm reading from a later slide, so what I would say is that you should look at the presenter notes, and that whole thing is actually going to be there. But there's a lot of good use cases for it. One is definitely volumetric clouds for environment curation. Okay, yeah, and that's been used in multiple games and film, actually. So one good example of volumetric clouds is Horizon Zero Dawn has them. They're artistically directed, and you can modify them as an artist in, approximately real time, if I remember correctly. You can read more about that in Advances in Real-Time Rendering, the rendering link over there. Pixar's The Good Dinosaur also uses 3D volumetric clouds as well. I think they utilize it in a very different way, but the idea is that the clouds are as realistic as possible. Pretty much the same principle. You can use it for you can use volumetrics for occluded scattering, so you can use it for volumetric shadows and live shafts, as you can see in the top left in the Uncharted 4 pick, which I guess by now everybody thinks I'd probably love Uncharted 4 or something. You can also use it for heterogeneous participating media as well, sun-particle interaction, physically based sky and atmosphere simulation, and large-scale fog, as I previously mentioned. And so one particularly interesting, and I thought this was cool because this is kind of the flip side of dealing with kind of how do you deal with physically based rendering for in terms of volumetrics, is that Uncharted 4, again, I guess my favorite game at this point, utilizes created some fabric and shader libraries meant to complement these new techniques. So they utilize that for their character pipeline, composed of finely granular assets that can be rendered out in real time, which is kind of really cool. Again, you should read those slides. They go in detail in terms of how they approach that process, and it's awesome. So we have some WebGL examples as well. I'm going to leave it to Xavier to actually talk about that, if that's okay.
Yeah, sure.
Yeah.
So on the left-hand side, it's a X-ray for the foot bones, obviously. But what they've done is they've loaded a 256 by 256 by 256 into a simulated 3D texture. So this was done in WebGL 1, they've done two deferred rendering passes, one from the forward and one from the back. And what that means is they can know where the back of the, shall we say, the volume is. Then they cast from the forward back by doing steps to figure out what color it is, and then accumulate the colors and then render it to the screen. So how they've done that back in WebGL 1 was they just created 256 textures and do all the things. It's really crazy. But in WebGL 2 now, it's like you can do that natively in 3D textures, which is really great. And then in the middle is taken from shader toy. That's just a ray-matched volumetric. So you have some fine distance fields with some fading parameters, and as you cast rays, you can still accumulate and you blend it into the background for a depth. So it gets darker or takes a different color and so on. But in volumetric, I think a more interesting example beyond just like clouds and volumes is also the visualization of flow, which is on the right-hand side. This was a company that was commissioned by Boeing, and they wanted to find out what the aerodynamics is like for this particular jet. And so I guess they probably did some wind simulations as the airplane flies or something, and then they can generate the flows of the particle in the volumetric bit, and then they do a raycast to show you what it actually looks like, which has a really compelling case of being able to figure out like where things are around 3D space, and you can kind of rotate around and see everything. And every data set is kind of in your GPU, which is really cool. And also, the next bit is going to be talking about the GLSO 3.0, which kind of ties in a little bit with volumetrics. So when you're using WebGL 2, it supports a new shaded language version, which is 3.0 ES. So on your first line, you'll be using that. And if you don't have that on your first line, the compiler will assume that you're using version 1. Or if it sees version 300 ES later, it will fail actually. So if you want to use the new features, including getting 3D textures, you have to have that line there. And then you can do all the cool things like, maybe I want to do the flow simulation, I've done my calculations, and I know exactly where the positive and the negative and different values are. I just have to put it into the GPU and render it, right? So once you have those data sets, you can set the textures at once. If you have all the buffer, you can just transfer from the CPU before the render stage. But if you want to modify it with, say, transform feedback, or if you want to modify it in a rendering GPU stage, you can just use the direct texture lookup and get it from the texture. You can assign it to a different buffer if you want it, and you can actually get the individual components too, and you can do all your awesome combining and sizzling stuff. So you can just take the sampler, which will be the texture. The UV coordinates might be, X, Y, Z of your WTV, whatever it is, on your 3D space, and then you can get the values out of that. And also, in addition to that, you can also say, I want my materials to be interpolated because it's 3D per geometry, perhaps with a triangle. That can be the smooth shading, which is the default, but you can also make it flat shaded. So if you wanted to have a really polygonal look and you want to put in shaders, you can just get that for free. And it comes with all the other awesome stuff. So like you can transform with non-square matrices. So you can do, instead of just 3x3 or 4x4 matrices for a fine and heterogeneous transformation, you can also do 4x3 if you want to save on some memory and you might not need the last row, for example. So there's a lot more cool stuff, and you can get the spec in the slides just linked there. That last update was 2016, so it's pretty relevant. And you will see that going to be a larger set to what OpenGL ES3 supports, but the ES3 is like the, I guess, the parent framework, but the GLSO, the shading language, is taken and based on that. Okay, so the next bit that we're going to is the survey of the industry, see how we're doing in terms of WebGL and where the adaptation is. And we're going to be talking about, first of all, what frameworks can we use, because I think if you're going to be a developer, you might want to find out how can we use it today, right? So Play Canvas, they have a commercial engine that you can already use today. I think it's not free though if you want to have any private repos. The only free one is you have to host it on their website. But it supports most of the WebGL 2 features from extensions with WebGL 1, and it's quite powerful. So like the previous mentioned demo after a flood was built in Play Canvas, and you can run on the browser and the phone, it just works. The next one is Blend for Web. As you may have guessed, it's an engine that was basically catered for the Blender community. So they built it so far ahead, now you can actually have Blend for Web inside Blender, which is pretty awesome, and you can have all the features that you developed in Blender, you can develop and preview, and then you can export to it. So you can say, here's my Blender file or whatever it is, and you will just play it as a viewer, and you'll be able to play all the animations and textures and whatever you got there. If you are into coding shaders with Icon shaders, Shader Tool is a really good place to go. they've had WebGL 2 for a long time. It's not quite there yet, but I put it here because they support all the extensions that WebGL 1 has. So if you want to do any buffers, deferred rendering, you can already do that for a long time. And they give you awesome, I guess, coordinates for the textures, your mouse position, you can load music. They have a lot of extra input that you can just get for free, and you can input your own music from SoundCloud and so on. It doesn't require you to do extra work. You can really focus on just coding the fragment shaders. So on the top left of that image was a elevation demo done in Shader Clay. So there's other frameworks that's intended to support WebGL 2 as well, and we'll talk about this again at the end of the presentation, but Three.js is probably the included information here. They've got a WebGL 2 renderer since, I think, February or something, but at the moment the renderer is not complete, so if you want to use it, you will have to either support your own WebGL 2 context from a canvas, you pass it to Three.js and say use this, or you just have to wait. So they're decided that because WebGL 2 is not entirely backwards compatible with WebGL 1, they're not going to have a mode switch in Three.js, so they're going to re-implement the renderer from scratch, which means if you want to use the full feature as the renderer itself, you have to wait for a couple months. But if you just want the extensions with instance rendering and deferred rendering, you can already do that with the extensions, so you don't have to wait. And other frameworks like Babylon and Whitestone A-Frame, that either depends on Three.js or they have to push their own rendering implementation as well. So I think you'll see with new APIs come out, say in April or March, it usually takes the community another 6 months to develop and implement the stuff on it. So that's pretty natural. And the next bit I will talk about after the flood, but I'll hand it to Juan.
Oh, okay, cool. So After the Flood is really cool. As I mentioned previously, it does several different things, or showcases several different things that are utilizing features from WebGL 2. And so that includes, using 3D textures for procedural clouds, procedural water ripples and reflections, animated trees, dynamic lighting, of course. The leaf particle system is derived from transform feedback. They utilize alpha to coverage in order to get around the process of being able to anti-alias the foliage. They use high dynamic range rendering, anti-MSA, which is an anti-aliasing technique, in order to be able to again do the anti-aliasing for the HDR surfaces. They have some techniques for shadow filtering, compressed textures, asynchronous asset streaming, so that they can have all of this working on the web, runtime light map making, and planar mirrors, so that they can have mirrored surfaces as well. Again, we're probably not going to play the actual demo itself. I would recommend playing or checking it out, but we can play the video. Do we have time for video, you think?
Yeah, we can play for a couple minutes.
Okay, we should do the video. It's really cool. It's like one of those, I think it came out in January, and I was like, oh my gosh, this is crazy.
Assuming my internet lets me play the video. Oh, looks like it's buffered.
Yeah, it's a collaboration between Mozilla and Play Canvas in order to showcase stuff, so.
You can definitely see the volumetric cloud on the top.
Yeah, that's one of the first things I paid attention to.
Yep. All right.
Yeah.
So the next bit will be about arts and performances.
Yes. Okay. So WebGL is also used for arts and performances, and this is kind of like an environment that I think could benefit from a lot more utilization of the technology. A few people have done stuff, or quite a few people have done stuff, but these are just a few of them. There's one that's been done in WebGL 1.0, which is just a reflector, which is done in 2013. It's a collaboration between Arcade Fire and Google Data Arts to be able to create this interesting multimedia project. A current one that's been done is called Project Sun by Philip Schutt. It's in collaboration with the Venice Art Project. And it's the GIF over there. And basically what it is that you have a ball, a real ball, that you can manipulate around, and in turn, what you see on the projected on the screen, what's being rendered, follows the movement of that ball itself. So you should check out the video for that. Stream, I believe, is done by Ezra Miller for Houston's Day for Night Festival. It is a WebGL implementation of streaming art and data visualization. I think it's just streaming art. There's an HTC Vive projection mapping, dance performance that was done in WebVR by Tianhun Marpi for Dance Hack Day. And basically it utilizes what, allows the dancer to kind of create WebGL or WebVR visualizations using HTC Vive and whatever peripheral they have available. The virtual art sessions from the Google Tilt Brush team took about 8 artists and just gave them a tilt brush and see what they could do, they can implement, and they've showcased that through WebVR as well. And finally, this is actually a plug. Basically, I'm doing a WebGL, why is it WebGL 2? A WebGL laser light show. I would omit the 2 just in case I don't do it in WebGL 2 because I don't know if I have time. But basically, I'm doing a laser light show that maps WebGL to a laser, and it's a performance piece with a composer for WebFest 2017. It's not announced yet, but it's going to happen. So those are some cases of where WebGL can be utilized for arts and performances.
Yeah, and in addition to that, WebGL has been used for data visualization as well. So I think the coolest example was the top left. You can see the white and green and blue. That was actually done in Flash before, and the company Gen 3 decided, hey, WebGL is out. We should just port it to WebGL. Right? So they have this awesome experience where you can see it's a conservation of bears in Canada, and that was also funded by the Canada, I think, the film and also the National Foundation or something like that, where they've been tracking bears as scientists. They want to find out where the bears go, what their habitat's like. So they got the elevation data for a certain national forest. Then they tracked a couple bears, and you can kind of look at the points that go around. You can follow the dots, and you can see a video footage when you mouse over them. You can see and check out how they sort of live around that area in different parts of the season. And you can kind of understand why bears need that forest to survive. And that was a really cool port. And so I guess a lot of really cool stuff with WebGL is that because you're rendering through buffers, you're not rendering through DOM elements, you can have a lot of points like with instance rendering, but also on the top right, that was a library called Regal, and they do this stateless WebGL thing where I think every frame they just send stuff to the GPU and they just push for boundaries as much as they can, and they've got a demo where they can just transform points in all kinds of awesome configurations, and you should definitely check it out. On the bottom left, that's the DeckGL, which you may be familiar with, done by Uber, and they're really keen on figuring out where the drivers are, how the city is doing, and how the traffic flows. But in this case, they've done a visualization with flights around Europe. So it's a bit dark on the projector, but that's the bright point is actually London, and they just have planes that fly out, and they use public data sets to figure out where the flight goes, and they can tell you the different time and what the condensing for population density is, for the flights. On the bottom right, you may be familiar with Google Earth VR. So Google Earth has been around for the longest time. You can get it on a desktop. But a couple months ago, they ported everything to the web, which I think is super, super exciting, and I'll show you as well. So if you haven't seen it before, definitely go and check it out. You can just play it with on your computer. So I think with this one, I can just go to... I don't have a device here, so I may not be able to use it. I can show the video. It's really fun.
I heard people cry when they used it, so.
It feels like Superman. You're like literally flying into Earth. So I should quickly point out this demo is actually done on the HTC Vive with Steam. It's not WebGL, but they do have a WebGL version, so I may have gotten the wrong link. Let me see. Google Earth. This is me live demo searching for stuff, which can be very, very good. So I'm going to do Google Earth, and I can launch Google Earth. That's the one I was looking for. And it may take a little bit of time to load. Oh, no, wow, internet's pretty cool here. Sweet. All right, let's get all those 4.5 billion years. Sweet. Okay, so let's just go to Brisbane, right? Because we're in Brisbane. So UT, nope. Queensland University of Technology. about that. Let's go there. So it goes right in, right? And because it's got elevation and Brisbane has obviously 3D terrains, it's able to render everything. Obviously not as comprehensive as the vibe demo you've just seen, but it's got all the Google Maps data sets that you can look around. And you can zoom in, you can rotate, you can search for places. You can do street view if you wanted. I don't know why, you can. So there's like spots in the Botanic Garden, and you'll be really familiar with this place. So that building is where we are. You can come in, and hopefully it just jumps into 360 videos or photos in this case. So WebGL has been able to do 360 photos for a long time, and you probably have heard yesterday that there is a 360 video or image working group as well in W3C. So that's going to be standardized pretty soon, and all of that is available on the web, which is really amazing. I'm going to put that. Yeah, feel free to check it out. I would really recommend check out how your hometown is doing, check out how your school is doing, and it's kind of crazy to see like your whole place in, I guess, 3D LiDAR scan reconstruction. Okay, close that. Right, another cool thing to check out if you're interested is ShipMap. So awarded as one of the, I guess, best websites for WebGL last year, 2016, where they've streamed, I think, 1 million points per frame.
At any given moment, tens of thousands.
To show that different shipping routes happen in different parts of the world and how that affects the world's economy. And the author does go around and kind of tell you about all the scenarios from the beginning of May all the way to the next year. And the map will just load with where it is, and the points will move around to kind of show you where the shipping routes was happening last year. So in this case, 2012, but the website was done last year. So I think it's a really cool website to kind of get a sense of how shipping works in our world today. So that's the aggregate of all the points. And my internet is struggling, so I might just close that. Cool. Lastly, if you do any data visualization with D3.js, one thing that may be very exciting to you is that Mike Bostock, the author of D3.js, did a demo where he connected D3 with 3.js. So D3 quickly is a data vis library that lets you interpolate data sets onto SVG, which is just a standard scalable vector graphics on the web. But in this case, he generates 3.js line segments out of D3. So you can now have, this is all rendered in WebGL now instead of SVG, and you have all the features that you like to use 3.js because that's all available to you. But you can get all your projections, geographical projections, you can get all your templations and domains and color scales in D3. So if you're familiar with both libraries, this may be really appealing and really powerful for you. Okay. So the next bit, we'll be talking about WebVR, and I'll hand it to Juan.
I think you muted.
Oh, okay.
Oh, did I mute him?
You muted it and the sound off.
Oh, yeah. Sorry, I'll put it back. Sorry, go on.
Okay, so, sure, no worries. So WebVR and WebAR is particularly interesting, right? So seeing a lot of device device adaptations are growing. There's 96% adaptation for WebGL, 37. This is, I guess these slides are a little outdated, but 37% adaptation. Really, I guess now 50% adaptation for WebGL 2.0. It's consistently growing. There's also WebVR, so you have the spec draft right over here, and it's slated for a Q3 2018 recommendation. And as of recent news, Firefox version 55 will ship WebVR by default. And that's going to happen around August. So everything is happening really quickly for WebVR and hopefully WebAR down the line as well. And sorry, my slides are a little out of sync here. And there's a bunch of cases for it, obviously, for the web. I think one of the coolest things about being able to do WebVR is again tied to the benefits of being able to do WebGL, which is that you can have it accessible anywhere potentially. And so we're going to talk a bit about some of the non-WebGL cases first before we dive into, WebGL cases that are already available that, showcase the potential of, WebVR and WebGL. And so some non-WebGL cases, of course, there are different setups. You have mobile 360, VR, AR, room scale VR, AR, and full body tracking as well. There's some cinematic and narrative experiences that are already available. One that has won a few awards is After Solitary, which is about the solitary confinement experience and what happens after. It's done by this emblematic group, which is run by Nani De La Pena, who is, I believe, the grandmother of VR. And Frontline, it's a conjunction with CBS Frontline, You should check it out. It won a few awards recently. I think at the World VR Forum. And this is a plug. There's also Pearl, which is our Google Spotlight Stories Academy Award nominated short about the father and the daughter and their car and their journey together. It'll make you cry. It made me cry multiple times, which I guess is how I ended up in Spotlight Stories. And there's all these other different cinematic experiences as well. There's of course some VR, gaming experiences, such as Job Simulator by Alchemy Labs, which was recently bought by Google. And there's just also Robot Recall, which was done by Epic Games. Slides back, please.
Yep, sorry.
And there are some virtual training simulation cases as well. There's the free flight safety check that Qantas does. International Space Station training by NASA. There's a really interesting. I have a really interesting. How do you say this? Case for this actually, where I believe VR was actually utilized for training, like for astronauts to prepare for themselves for being in in an enclosed environment. And so what they did was they grabbed like a bunch of astronauts and put them in Hawaii in a dome for 9 months, and they utilized VR as a way for them to communicate with the outside world. And actually, the engine that they utilized for it was actually not Unreal and not Unity, because they were running on a shoestring budget, or the company trying to build the system was running on a shoestring budget. But what was really cool is that despite the fact that it was really basic assets, the actual astronauts were still immersed in that environment. Maybe because it was the only environment available, but it was really cool that they were able to do that even for 9 months. I think they left themselves messages on trees or whatever. There was one guy who was a jokester and made like a giant tree house or something. But yeah, those are some cases where training simulation kind of goes out of control, but is utilized to be immersive, regardless of how much granular detail is available. Of course, from an AR perspective, there's an elevator maintenance Internet of Things case that's been done by CSIRO in collaboration with Microsoft, and basically it allows elevator maintenance workers to kind of check and see like how elevators are doing, and they have a proof of concept for it. Some other cases as well, if we go to the next slide, showcase art being done in WebVR or VR. So Steve Teeps is an artist in Oakland. He does a lot of installations using Oculus Medium and Tilt Brush, and if you see the top right picture, that's kind of one of his works. Time also did kind of a showcase on VR, how VR is utilized for art by artists, and they take very different artists who haven't utilized VR before and allow them to kind of play in the space. From a visualization perspective, KPMG has a HoloLens data analytics tool that was done in conjunction with KPMG Look, which is kind of, I think, a consultancy company, and Microsoft. There's also the virtual data visualization platform, which is kind of like by Virtual Analytics, which is analyzing data analytics in VR, immersive 3D VR. Social VR, of course, you've heard of Facebook Spaces demo where they, Mark Zuckerberg and a bunch of the leads are, in a social VR space. From the medical and health perspective, there's Advanced Imaging and Medical Modeling Program from OSF Healthcare, and what they've done is they've combined being able to play around and kind of learn more about, I believe, cardiovascular problems or the heart itself in VR, and tied that into 3D printing. And there's also a Luke Hand project, which I work with, and what they do is they utilize AR to kind of prototype and like a bionic hand, as well as kind of like allow there's one subject right now, to be able to play around and kind of do the training for getting used to using the bionic arm in AR. So those are some cases that are available that are kind of cool. And so from academic research, actually, in the next case, there's a bunch of research that's been done for years. I put together a list of some of the really cool ones, including a survey on augmented reality, and kind of like concepts and ideas about empathic computing and where that leads. VR has been mentioned to be the new empathy machine, and that particular article by Mark Billinghurst actually talks about why that is actually the case, and not necessarily the case of what that's being pushed forward by, I guess, by people in production. So that's a very interesting article. Mel Slater has done some really interesting work in terms of body semantics, implicit association tests in VR. The really cool one was putting yourself in the skin of a black avatar reduces implicit racial bias. And it's a really interesting concept because basically it really is just like you're a very different avatar, but you have to deal with the fact that how do you deal with it, being unconsciously aware that you're that avatar now, He also did work on body transfer virtual reality, which is really cool. And Google recently announced that they've done some research on headset removal, quote unquote, in virtual reality and mixed reality. And the whole idea is that you can see if you're kind of like in a 3D environment and you're looking at someone else, you can kind of see their face instead of just like the headset itself. So finally, there's some industry standardization happening. There's OpenXR by the Cronus Group, and I believe IEEE just announced their VR and AR standard development working group as well in order to be able to create these standards for these emerging mediums. So, and now Xavier is going to talk about VR and AR in Australia because obviously this is a global phenomenon. So.
Yeah. So if you have been to the VR hackathon just on the weekend, there's a company called Lightweave. They do lots of VR content, so like the Dinosaur VR licensable content. You can just go and check it out. Also, Zero Latency is based in Melbourne, so they just announced last month they have a simultaneous 8-player in the same room. You play as a, like, I guess, zombie shooter, or you're a space person trying to fight off robots. And they have 3 different scenarios that you can play, and you simultaneously co-locate in the same room. But what's really cool is that they play with your perception, so you can be like on the elevator, you feel like you're up here, they're down there, but in fact you're still in the same room, and they do really tricky things to kind of trick your senses there. Platter is an interesting company. I think they're based in Sydney. I could be wrong, but they have a bunch of AR apps that let you put in yourself. So they started out by filming people in green screens, and you can put yourself on your business card. So when you give someone your business card, you can also say, hey, down this app, I'm going to give you a picture of this on my card. You can check out my products and so on. But it's since expanded into home, lighting, furniture, different kind of product showcases and so on. And also there's Pixelcase, Immersia, VR12, and they're all media company productions that have been working with VR and AR and 360 videos. And so it's Start VR, I believe. PlaySide is a game company that just made a Zombie Riot game that I think just came out on Steam, so you can go check it out. Liminal VR does this meditation, psychedelic VR experience to both calm you and agitate you, as from what I've heard. And it's quite exciting. They're also based in Melbourne. Panorama Interactive does more like indoor finished stuff. So in this case, they're having architecture demo with just different kinds of scenes, and you can check it out as well. So it's a lot of them happening in Australia. It's too hard to list them all, but if you can check around the scene, there's many different cities, including Perth, and there's like all these companies going on. So it's cool. All right, I'm going to hand it back to Juan about AR and VR and what WebVR.
Absolutely. So, why WebAR and why WebVR? So again, as I mentioned previously, WebVR and WebAR are a very important part of the VR ecosystem. It kind of has, again, the benefits of WebGL for widespread cross-compatibility and adoption. And again, if you have even just the Google Cardboard, I guess you can totally be able to be immersed in that sort of, immersive environment. I wouldn't know about WebAR necessarily, but obviously WebVR. It works for every platform. WebVR specifications does not really distinguish what device you can use for it. It's, again, readily going to become available, like there's Firefox is going to be allowing it to be in, we'll be shipping with it for, their version coming in August, and Google has already support for WebVR and AR. And ultimately, I think that's kind of, it's a really good case for the propagation and distribution of this platforms, right? When you're looking at games like Robo Recall, for example, if you look at games like that that are high quality AAA titles, but cost just about as much as making a like Gears of War, the first Gears of War, which I believe is the budget that they announced was in line with creating that game, on top of like getting Oculus support. Like you're creating a lot of content. You're basically trying to create like content with a lot that requires a lot of like budgeting, requires a lot of manpower, that sort of thing. The thing that's really cool about using WebGL 2.0 and WebVR, being able to utilize WebVR, is that technology has been democratized and is available for people to use, and it is available for any device. And so the potential to be able to do many things, regardless of how much granularity of detail or high resolution experiences that you want to create, even if they're not to the level of a AAA game, it's available for you to do that, and you can do a lot of really cool things just based off like really basic things, like I said, the NASA experience where the astronauts were enclosed in a dome for 9 months. They believed that they were immersed, and they didn't require a lot of like really crazy stuff to make that happen. So it's just a matter of like application and having the right tool set for it. And so I'm going to toss it back to Xavier to talk about kind of like some of the frameworks that are available to be utilized for WebAR and WebVR. So.
Yeah, for sure. So if I don't know if Blair is in this room, he did Target, right? He's downstairs. Yeah. So you can already use it. It's on version 4. You can download it on both iPhone and Android, and they've got a bunch of demos both natively on the phone and also using HTML5 well, I think mostly HTML5 but wrapped around. You can do feature tracking. You can track markers, so you can add different content already. That's pretty cool. I think A-Frame is probably the most well-known one, where you can just use this tag-like, I guess, markup language to load different entity and components like OBJ files and different things. You can describe lights and everything in text, and the browser will just render them in an AR, VR, or just a normal scene. So they've been compatible with WebVR since pretty much day one with the polyfill, so I recommend checking that out. But the crazy one is probably the JS AR toolkit, where someone took the whole C++ library and just compiled it to JavaScript and go, here we go, we have AR. And the documentation is probably not the most user-friendly, but it is pretty powerful and pretty damn fast. So especially if you have Firefox and WebAssembly, it's crazy. So yeah.
We also demonstrated OpenCV working in the browser.
Ah, yes, of course. Yeah. So definitely talk about.
We're not letting any deal.
No, sorry. Yeah, I was making this like a long time ago. Sorry about that. Need to update the slide. Okay, so the next bit, I'm gonna hand it back to Juan.
Okay, well, WebVR, WebAR, WebVR is happening. That's literally the title of the slide. Sorry, I just literally read that. And there's a lot of already applications for it. So obviously there's going to be the VR web browser. Google Chrome is coming to AR and Daydream. They've announced that they're going to do a significant update towards doing that. So instead of like having Chrome on your, the regular Chrome browser and trying to do VR experiences from there, they're going to give you Chrome in a VR context. Similarly, Oculus has their Carmel WebVR browser. There is, if you want to look at something really cool, there's the WebVR NYC Snow Globe, which basically, if you click on that link, you can, and we should click on that link now. Do we have time to click on links?
Yep, sure.
Okay, so if you click on that link, you go in and you can kind of like, obviously we won't be able to do it because we don't have a device available, but you can manipulate and go really close and kind of see like this New York City snow globe. I feel like this was just done really recently. So let's go back. And okay, so other utilizations. There's one of the first. I don't know if it's one of the first, but definitely this is the one that went to Tribeca. There's Broken Night VR, which was purely done in WebVR. It involved Emily Mortimer in a suspense, choose-your-own-adventure thriller VR filmic experience. So that's kind of what they pitched for. It seems really cool. Web Screen VR allows you, by Samuel Cadillo, allows you to kind of like expand your space in the WebVR environment. There's a bunch of WebVR experiments that Google has done so far. There's Wayfair has created a Google I/O 2017 prototype, and obviously they have their GitHub available, so you can check that out. And I believe, no, this is the WebAR, sorry, yeah, so you can actually be able to manipulate and put objects or furniture in, an augmented reality space. Some really cool hacks includes a posture recognition hack using Connect, the Azure Internet of Things, machine learning and WebVR, and you should click on that link. Ron Dugdug goes into detail in terms of how he implemented it. There's Band Explorer VR, which allows you to kind of do Spotify in VR. There's a virtually WebVR hackathon where people are actually trying to pursue creating these hackathons for people to try out and make experiences utilizing specifically WebVR. There's a bunch of people involved in that, including some people who are keynotes at Web3D just recently. And finally, A-Frame has their school which is their interactive course for WebVR, which they teach you how to utilize A-Frame to create WebVR experiences. So there's a bunch of different things that are happening right now in that sort of ecosystem that is very encouraging for people to come in and try out. So what's coming in the future for WebGL now that we can pull ourselves back from the VR AR discussion? So ultimately, the web is a publishing platform, right? So, and with WebGL power rendering, a lot of things that we want to do in terms of graphics and mixed reality experiences are going to be feasible, or already are feasible. So there's definitely a lot of the things we discussed is all about not just the potential, but also how we can converge towards those applications. Many libraries are already implementing WebGL 2.0 support. 3JS definitely has their WebGL 2 renderer, as Xavier has mentioned. That's already, I believe, if I understand correctly, they're working on that in parallel to having their WebGL 1 renderer development, just because the architecture is very different. I actually had lunch with one of the Shader Toy folks, and I think they're trying to do something relatively similar, and they were kind of in the process of dealing with it, but obviously because the architecture is very different, that I think their take on it is that may not be able to like implement everything right off the bat. But again, the library, everyone who's working on these libraries are paying attention to WebGL 2 and trying to support it. In the future, I think one of the goals is to have compute shaders available in WebGL 2.0, which will allow you to do multiple things. GPG, you can do general purpose GPU computations, which then expands kind of what sort of things you're able to do on the web. You can do parallel data structures, ray tracing. You can play around with artificial intelligence, neural networks, that sort of thing. So think about kind of like what the possibilities are in that realm and having that available to you guys easily through a democratized technology. WebGL Next is probably going to come in the future, or it's going to come in the future for sure. It will continue to bridge the gap between graphics drivers and the web. That being said, the caveat is that WebGL 2 just came out, right? So the focus is really on having that have widespread adoption and growth. And ultimately, people are still figuring out what's next for this particular iteration, as well as where we should be trending towards in the future. So it's still early days for that. What things that people are trying to look into is they're trying to understand, trying to get towards a pre-validated design for the API so that it reduces draw call overhead, which means looking at the next generation APIs, Metal, Vulkan, DX12, and seeing what they can bring to the table such that we can ultimately eliminate the class of issues that are already associated with OpenGL. And a good place to look for that is GPU for the web community, because they engage in those type of discussions, and it's a great place to kind of get your feet wet and kind of learn more about where things are going, as well as get to know people. So that's it in terms of what's coming in the future, and I guess that's a wrap for the most part. We can talk about the conclusions and resources. So in conclusion, WebGL 2.0 exposes OpenGL ES, the OpenGL ES 3.0 feature set, right? You get textures, you get transfer feedback, texture support, or more texture support. You get transfer feedback, multiple draw buffers, or multiple render targets, same thing, to enable efficient graphics rendering. It's really all about a lot of the optimizations that you can do and the techniques that you can finally pursue with these optimizations. We talked a bit about forward versus deferred rendering. We talked about volumetrics, geometry instancing, some cool things you can do with those particular techniques. And there were things that we actually didn't get to, which I guess is, non-power 2 textures, at least not in terms of examples. And ultimately, WebGL empowers many fields of practice, right? You can do real-time games, real-time cinematic experiences, data visualization, performance arts. You have WebAR and WebVR at your disposal. It's already supported by major companies and platforms, and it's available for it has a lot of frameworks you can choose from in order to start. So ultimately, the real question coming from this is, given all this access to graphics technology and ideas, what can you create? What will we create next? So, and if we go to the final slide.
Yep, you can get the slide from that link. It's tinyurl.com/web3d 2017-WebGL2. If you want to try out the WebGL 2 API and you kind of want, come about it with the really verbose, raw code just to get a triangle on the scene, you can look at picogl.js. So someone has wrapped WebGL 2 in a very, very thin wrapper. You still have to create your own buffers. You still have to send the data sets, and you still have to write your own shaders. But you don't have to bind everything over and over again and compile shaders. So it's a little bit easier to get into, and you'll definitely be really familiar with the API by the end of trying out the API examples. And also, there's a bunch of examples you can try out with React 3D. There's VR as well, and they've got a wrapper on top of the JS, and they've got examples to see how you can update scene graph with React if you're into that kind of HTML tag one-way data flow thing. And lastly, there is a community group in W3C called the GPU for the Web, which I think is going to drive a lot of what's coming up for the next generation GPU API. And personally, I've just learned about this community last week, so I'm really keen on finding out more as well. And Juan, can you talk about the CGraph bit?
Absolutely. So if you want to learn more about mobile graphics or just graphics in general and interactive techniques, there's SIGGRAPH, of course. ACM SIGGRAPH 2015 is happening this July 30th to August 3 in Los Angeles. And I can guarantee you they're doing some really interesting stuff for VR right now. They have a VR theater. They're taking in, I think, the emerging technologies, which is kind of like a venue where you can try out emerging technologies, has a lot of AR, VR experiences as well. And they're just talking about some really cool stuff. Personally think you guys should go to ACM SIGGRAPH Asia 2017 Bangkok. And it's not, and one of the reasons, of course, I'm going to plug is I am the VR AR showcase chair. We're planning to ramp up and have a lot of experiences available in Bangkok, Thailand for people to try out. And there's also the Symposium for Mobile Graphics and Interactive Applications as well, which was more in line in terms of like where mobile graphics is going in terms of what the technology is and applications. So.
Yeah, so we want to thank everyone who's put the stuff that we'll be including in the slides, as well as giving us feedback and putting everything together. And there's a lot of people to thank. So, yeah, just on and on. Okay, so that will be a wrap, and I think we have 4 minutes for questions.